Can you see my slide?
All good.
Okay. Thank you for your kind introduction, Jack. And I'm very excited to share this research about hydrogen in front of audience who's very interested in methane. And this is because hydrogen and methane are closely linked together, and I'll show you more of that through this presentation. There are three types of hydrogen, and we usually classify it based on the color. And the gray hydrogen, as you can imply from the name, has a lot of the climate impact. We produce hydrogen from natural gas using steam methane reforming, and primary climate forcers emitted in this technology will be CO2 and methane. And next, we have blue hydrogen, and this is exactly the same technology as gray hydrogen, but with carbon capture usage and storage technology. So we will minimize the CO2 emission, but still there will be some residual CO2 methane emitted, and we will also have hydrogen leakage during the process. And for blue hydrogen, we call this low carbon because we now do the carbon capture. And lastly, it's green hydrogen. And as you can infer from the name, this is known as zero carbon or climate neutral. And this is because we are using renewable electricity to undergo electrolysis and form hydrogen. So this doesn't emit any CO2 or methane, and it only emits possibly hydrogen. And since hydrogen it itself, it's not a greenhouse gas, people usually think this is a climate neutral solution for our future. But before we dive into hydrogen's chemistry, we will just think about hydrogen as it is. Hydrogen molecule, if you kind of imagine the periodic table, the element has the lowest molecular weight of 1, and it has a very symmetric shape, just two hydrogen atoms attached to each other. Because of the symmetry, they don't absorb any infrared radiation. But the problem of hydrogen is that because it's so light and highly diffusible, it leaks very easily through a lot of the pipes, through small cracks. And also, there is what's called the hydrogen embrittlement, where for certain materials like high strength steel, hydrogen can actually lead to weakening the material and more leakage and possibly even to explosion. So the question we really need to ask when we think about hydrogen's technology is how are we going to detect this leakage? And also, how are we going to minimize this leakage? And 2 weeks ago, Dr. Zutao Yang gave a great talk about hydrogen budget. And the key main takeaway from his talk was that current day, the methane oxidation is a major source of hydrogen. But in the future, when we adopt hydrogen's economy, hydrogen leakage into the atmosphere will be future sources of atmospheric hydrogen. And once hydrogen is emitted into the atmosphere, about 80% gets removed by the deposition to soils. And this is quite different from methane, where only 10% is removed by soil. And rest of the 20% reacts with OH, or hydroxyl radical. And OH, you can really think of it as a Pac-Man of the atmosphere. It reacts with various chemical species in the atmosphere and remove that chemical species. So you can think hydrogen as one of the monster that Pac-Man reacts. And through this reaction, we eventually form just H atom and water molecule. And if you just look at this equation, you might think, okay, it just produces H atom and water molecule. So what's the deal? Why is it a climate forcer? And this is because of the reaction with OH. Essentially, methane is also removed by OH in the atmosphere, about 90%. And if we are adding more hydrogen into the atmosphere, methane and hydrogen has to compete for OH, and this in return will increase methane's lifetime and concentration of methane in the atmosphere. And H atom also readily reacts with O2 to form HO2, which is an important precursor of tropospheric ozone. And tropospheric ozone is important air pollutant that impacts our health, but it is also a climate forcer. And lastly, stratospheric water vapor is also another greenhouse gas. So you can see from this reaction with OH, hydrogen actually leads to increase in three important greenhouse gases. And this is what makes hydrogen an indirect climate forcer. And the lifetime of hydrogen is much shorter than methane. It's about 2 years, whereas methane is 12 years and CO2 is 100 years. And common way that we quantify the climate impact of a particular gas relative to CO2 is what's called the global warming potential. And you can think of global warming potential of what does the 1 kilogram pulse emission of hydrogen, what is that radiative forcing relative to 1 kilogram pulse emission of CO2? And it is an integrated radiative forcing. And for hydrogen, this impact will come from increase in methane, tropospheric ozone, as well as stratospheric water vapor. And global warming potential can be defined over different time frame. It can be either defined in 20-year time frame or 100 or even 200. And for short-lived climate forcers like hydrogen and methane, the global warming potential over 20 years will be about 3 times higher than the global warming potential over 100 years. And global warming potential is definitely not the best matrix out there because it is only quantifying the pulse emission, whereas in reality, it's a constant emission. But since global warming potential over 100 years is baked into our policy discussion about climate, we are sticking with global warming potential over 100 years for this study. And our current consensus of global warming potential over 100 years of hydrogen is about 11.4. And 44% of that effect is from methane, 38% from ozone, and 18% from water. And this work is using a 5 different ensemble 3D models from Send et al. Estimate. But if you can see from this range, other studies actually sometimes estimated to be lower than that, especially for the 2D model, Derwin et al. Estimated it to be about 8. From photochemical box model, the value was estimated about 10. And in the individual 3D models, which is represented by Warwick and Hogolstand, this value was 12 to 12.8. And using the 5 different ensemble 3D models, the value was 11.4. And you can see this discrepancy of simplistic model versus 3D models. And this is because for 2D and box model, we can effectively parametritize the OH concentration. But for 3D models, this is harder. It's driven by emission, chemistry, and transport. And as I will show later, this overestimate in 3D models is due to OH bias in our 3D models. And OH not only reacts with hydrogen and methane in the atmosphere, in reality, it reacts with thousands of chemical species in the atmosphere. And you can kind of imagine these other species as thousands of different ghosts that OH will consume. And because of this, lifetime of OH is extremely short in the time scale about 1 second, and it is very hard to measure it directly. So what we do is we infer OH concentration using methane lifetime against OH. We can express methane lifetime against OH as methane burden divided by the loss by OH. And this loss rate can be represented as rate constant times concentration of OH times concentration of methane. And if we substitute this loss rate into the methane lifetime equation, we will get this relationship that concentration of OH is inversely related to methane lifetime. And luckily, methane lifetime against tropospheric OH is well constrained using observational methyl chloroform proxy, and that value is about 11.2 years. So if our model has a shorter methane lifetime than 11.2 years, it indicates that our model has too high of a OH concentration and vice versa. And when we investigate this five different model ensemble that estimated the current consensus of global warming potential, the methane lifetime against tropospheric OH is about 8.3 years. And from three individual 3D models like GFDL, UKESM, and GeoSChem, the value ranges from 8.5 to 9.5 years. And lastly, from 17 ensemble model, ACMID multi-model estimate this value to be in the close range of these other models. But the methyl chloroform proxy estimates it to be about 11.2, and even if we account for the uncertainty range, model underestimated by 10 to 30%. This in return means that models really overestimate tropospheric OH by the same magnitude. And this OH bias can eventually lead to biases in our hydrogen global warming potential estimate. And the trouble with model is that it cannot represent all of the chemical species reacting with OH. Sometimes we might be missing some of the important volatile organic compounds. Sometimes we might underaccount for carbon monoxide emissions. And OH reactivity is a matrix that really represents OH loss frequency. And you can think of it as a total OH loss frequency. And we can obtain it by simply multiplying the rate constant by concentration of reactant that reacts with OH. So rate constant of hydrogen times concentration of hydrogen. We can do this for methane, volatile organic compounds, and so on. And the lifetime of OH will be inversely related to this loss rate. And when we compared our geoschem model to the observation of OH reactivity, during the Chorus AQ, which surveyed over South Korea polluted air, we saw about 60% underestimate in OH reactivity in the models. And when we compare against ATOM campaign, which surveyed over remote air, the OH reactivity underestimate was about 30%. And when we compare with the surface continental OH reactivity measurements, model underestimated by a factor of 2 to 10. And underestimated OH loss frequency, or OHR, means that we will have a longer OH lifetime and in return, higher OH concentration than in reality. But the problem that we are not only interested in is not just the absolute magnitude of OH, but really the perturbation or sensitivity of OH to perturbation of H2. And this is because hydrogen reacts with OH and that perturbs OH concentration, which impacts methane's lifetime, that changes the radiative forcing and gives the hydrogen's global warming potential. And if we assume steady state, the concentration of OH can be represented as production of OH divided by this total loss rate or OH reactivity. And if we want to find the sensitivity of OH to hydrogen perturbation, we can simply take the partial derivative and we can obtain this equation. So what this equation tells us is that sensitivity of OH to hydrogen is inversely related to square of OH reactivity. And in plain language, this means that if our model underestimate OH loss frequency by 30%, this can actually lead to 43% OH sensitivity overestimate. This means that OH role that it plays on sensitivity of OH and in return, methane lifetime and ozone production will be overestimated, leading to overestimated global warming potential of hydrogen. And in the standard geoschem model, when we looked at the OH reactivity over remote atmosphere, the OH reactivity was about 1.1, and methane accounted for about 19% of total OH loss, hydrogen about 6%. So together, methane and hydrogen accounted for about 25% of OH total loss. And what we did to reconcile the OH reactivity bias was we first added non-methane volatile organic compounds from volatile chemical products as well as oceanic emissions. And these were based on previous studies that hinted that these are the missing sources of volatile organic compounds in our models. However, the problem was that even when we added these, we couldn't fully reconcile the OH reactivity underestimate in the model. However, if we added more and more non-methane volatile organic compounds, we eventually had to compromise ozone concentration. We were producing too much ozone, and we didn't want to do that. So what we did was we added terminal OH sink over the continent as a constant value. And we are not claiming a mechanistic solution to fixing OH biases in these 3D models. That's a really fundamental question that our field is trying to answer. But simply what we wanted to do was what's the effect of fixing OH reactivity on global warming potential of hydrogen? And once we added these addition to our model and reconcile for OH reactivity against aircraft observations, the OH reactivity now increased from 1.1 to 1.57, and the contribution that methane and hydrogen plays as a OH sink decreases from 25% to 17%. Rather, now the added non-methane volatile organic compounds play more important role as OH sinks. So in summary, if we have less contribution from methane and hydrogen as OH sink, this means that sensitivity of OH to hydrogen perturbation will decrease, which in turn means that methane lifetime change from hydrogen perturbation will be smaller, which leads to lower hydrogen's global warming potential. And reconciling OH reactivity also reduces methane self-amplification. Methane has what's called a feedback factor. If you increase methane concentration, it will consume more OH, which leads to decrease in OH concentration, which increases methane lifetime and increase methane concentration even more. And this is called the methane feedback factor or self-amplification. And this quantity really represents the coupling between OH and methane. So when we compute methane's global warming potential, we not only care about just the lifetime of the methane, but we multiply that by this self-amplification factor and obtain perturbation lifetime. And this is what's used in the global warming potential calculation. And this table lays out how does the perturbation lifetime, feedback factor, and total lifetime of methane, as well as methane lifetime against tropospheric ozone looks like in different models. Multi-model ensemble is that 5 ensemble model that estimated the current consensus global warming potential. We also have standard geoschem, which has the same OH overestimate issue, modified geoschem where we reconcile the OH reactivity bias, and IPCC AR5, which uses the observational constraint value. Let's begin with the lifetime against tropospheric OH. In the IPCC report, they use the methane lifetime that's constrained by the methyl chloroform proxy, and it was 11.2. And both in the multi-model and standard geoschem, because they underestimate OH reactivity, they have a shorter lifetime. But once we reconcile for that OH reactivity, we now better match with the observationally constrained value of 11.2. Total methane lifetime is simply accounting for additional minor sinks of methane, which includes stratospheric oxidation as well as soil sink. And for the feedback factor, in the IPCC report, it reported 1.34, but in the multi-model ensemble and standard geoschem, these values are a little bit higher. And this is because in these models, they have excessive coupling between multi-model ensemble and standard geoschem model. And in the modified model, we have a weakened coupling between methane and OH, which leads to lower methane feedback factor. And the perturbation lifetime is once we multiply with the feedback factor and the total lifetime of methane. So what this shows us is that by reconciling the OH reactivity, we actually weaken the methane and OH coupling, and the lifetime of methane now better matches with the IPCC report. And now let's move into the effect of these changes to tropospheric ozone. The pathway in which ozone can be formed is through three different pathways. NO can either react with CH3O2, HO2, or RO2. And CH3O2 is mainly formed from methane oxidation. And HO2, hydrogen contributes by a small amount, as you can see from this reaction. This H readily reacts with HO2 to form HO2. And lastly, RO2, which represents other peroxy radicals, and this is formed via non-methane volatile organic compounds oxidation. And in the standard geoschem model, the role that methane oxidation plays in OH loss, ozone formation is large, is 25%. But in the modified geoschem model, this decreases to 23%. And one thing we need to note is that the role that RO2 plays, or non-methane volatile compound plays to ozone production, now increases from 6% to 15%. And contribution from HO2 decreases by 7%. So what this means is that since we added the non-methane volatile organic compounds into our model, as well as that terminal sinks, now the role that methane as well as hydrogen play in ozone production is lowered, and their contribution to ozone production is thus lower. And this is the bar chart that compares how multimodal ensemble estimate compares with the standard geoschem model and the one that reconciles the OH reactivity. In the multi-model ensemble, the value was estimated to be about 11.4, and standard geoschem model agrees closely with this with the value of 10.8. But in the modified model, this global warming potential decreases by about 20%. And methane contribution decreases by about 17%. And this is simply because now OH is less sensitive to hydrogen's perturbation. But ozone effect is more than 30%. The reduction is more than 30%. And this is because, first of all, hydrogen now plays less important role in formation of ozone. And now non-methane VOCs play more important role in ozone formation. But second effect that compounds this is that since now methane changes is weaker than before to hydrogen's perturbation, now that methane forms less of ozone as well. So this is a compounded effect for the ozone, and that's why the reduction is larger. And after hearing this talk, what I've shown is that our estimate now is about 20% lower. And what this work did was that we kind of reconciled the differences that we were seeing in 2D box models to 3D models. But you might ask this question, okay, it's 20% lower, but still the global warming potential is not one. So why do we even bother thinking about hydrogen's technology? Why don't we just stick to traditional energy source? And this is a really valid concern, but I want to emphasize that the promising future of hydrogen fuel all depends on the leakage rate. As long as we can contain that leakage rate, hydrogen's warming potential will be significantly lower. And Oko and Hamburg et al. Kind of calculated this for us already. And they consider both optimistic and pessimistic scenarios for green hydrogen as well as blue hydrogen. For green hydrogen, when they assume 1% leakage, within 10 years, there will be 95% decrease in warming, which is very promising. But in the worst case scenario, if you have 10% leakage, this effect will be weakened, but we will still achieve 60% less warming than the traditional fossil fuel sources. And in case of the blue hydrogen, in the optimistic scenario, when we only have 1% leakage for both methane and hydrogen, this will lead to 65% warming within 10 years. And you can see this is comparable to green hydrogen's pessimistic scenario. But in case of the worst case scenario where we will have 3% leakage in methane and 10% leakage in hydrogen, we actually have 40% more warming than sticking with traditional fossil fuel sources. So what this really tells us is that we as a community together will work to move towards minimizing the leakage and maximizing the climate benefit of green hydrogen and try to avoid this worst case scenario of the large leakage of the blue hydrogen. And hydrogen's emission rate remains highly uncertain due to lack of field measurements. This paper kind of shows hydrogen's emission rate at different pipelines from production, conversion, transport, storage, and end use. And different shape shows how the estimate was made. It can either be assumption, which shown in triangle, or model simulation. And what you can see from here is that in the transport stage, hydrogen emission rate can range from 10 to 20%. And this really shows that perhaps hydrogen should be deployed in a sector where we produce on site and use it rather than we produce hydrogen and transport long range, leading to this risk of hydrogen's leakage happening. So we have many brilliant minds in this audience, and I want to kind of challenge us to think together about what we can do as a community. I think in terms of the measurement side, the leakage detection is very important. We have to monitor where the leakages occur in different pipeline and better understand that rate. And also, soil sink is another huge uncertainty when it comes to estimating the climate impact of hydrogen, so we need to study more on that aspect. In terms of the modeling side, we have to definitely better understand OH chemistry to better understand that OH methane hydrogen coupling effect. We also have to work with soil sink uncertainty. And we should also start to think about what if hydrogen is emitted in the northern hemisphere versus southern hemisphere, because emission location will matter. And lastly, what if hydrogen is emitted with other air pollutants like NOx? Like, does it have any feedback effects? And what does hydrogen economy mean when we have methane background reducing? How would that feedback into hydrogen's climate impact? And on the industry side, we have lot of hope because this hydrogen technology is still in the early stage. We are still, if we think about the design stage, starting from the beginning, we can think about how are we going to design so that we can minimize the leakage, and how are we going to monitor and design it so that it doesn't lead to warming effect that we don't want it to have. These are the takeaways of my talk. The key is that OH reactivity bias in the model leads to excessive coupling between OH, methane, and hydrogen, leading to exaggerated hydrogen's warming potential. And what we've shown is that by correcting this bias, we were able to reduce the global warming potential of hydrogen by about 20%. But we still need better understanding of factors that controls OH concentration and OH reactivity. The Navy QR code shows the journal article that is based on this presentation. And I also have a contact information, and orange QR code shows my personal website. I'm very excited to talk about future fuels and its implication on oxidant chemistry. So please feel free to email me or reach out to me at your convenience if you have any questions or collaboration opportunities.